Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are undertaking a deep dive into the fundamentals of gear design.
Mm,
And we're not just talking definitions here. Our mission is really to get into the calculations, the
yeah.
trade-offs, what it takes to design a reliable gear train. We'll be leaning pretty heavily on the AGMA standards, the American Gear Manufacturers Association ones.
Yeah, it's a great topic. I mean, gears are incredibly old tech, right? Over 3,000 years, they're everywhere, from ancient clocks right up to modern rockets. And their main job is always controlling speed, RPM, and force, which is torque.
Right. And the precision, that comes down to the tooth shape, doesn't it? We always hear about the involute curve. Why is that shape so important?
Ah, the involute. Well, fundamentally, it's the path you'd trace if you unwound a string from a cylinder. Think about the end of that string. The reason it's essential is that it's the only shape that guarantees a constant velocity ratio as the teeth mesh. And maybe more importantly, it really maximizes that smooth, pure rolling motion between the teeth. It minimizes sliding.
Okay, so maximizing rolling, that's the key to the high efficiency we see, the secret sauce.
That's it, exactly. For typical spur gears, the efficiencies are remarkably high, often up there with good anti-friction bearings. We're talking high 90% range usually.
Okay, let's get some basic terms down. When you have two gears meshing,
Mm-hmm.
the smaller one's the pinion, the larger one's the gear. Always.
Always. Doesn't matter which one is driving the other. Pinions smaller, gears bigger.
Got it. And the ratio is just teeth on the gear divided by teeth on the pinion?
Yep. Simple division.
And it all seems to relate back to the pitch diameter.
Absolutely. The pitch diameter is the sort of fundamental reference circle for all the geometry. And just like the tooth count, if you divide the gear's pitch diameter by the pinion's pitch diameter, you get the ratio again.
Okay, so diameters give the ratio. But how do we define the actual size of the teeth themselves? This is where we hit that metric versus imperial thing again, right?
That's right. It's a classic split. In the English or U.S. customary system, we use diametral pitch. We write it P sub D, and it's defined as the number of teeth divided by the pitch diameter in inches.
So P sub D, and it's kind of counterintuitive. Lower number means bigger teeth.
Exactly. A low P sub D, like maybe 1/2, means really large teeth. A high P sub D, say 200, means tiny, tiny teeth.
Okay. And the metric approach.
Metric uses the module, just written as M, and module is the pitch diameter, this time in millimeters, divided by the number of teeth.
So module M is more direct.
Yeah.
Bigger number, bigger teeth.
Yeah, much more straightforward. A small module, like 0.2, is a small tooth. A large module, maybe up to 50, is a very large tooth.
Let's zoom in on a single tooth. There's the addendum
That's the height above the pitch circle.
and the dedendum.
That's the depth below the pitch circle.
And if you add them together,
That gives you the whole depth of the tooth space. For standard teeth, a quick way to estimate it is just 2.250 divided by the diametral pitch, P sub D. That little bit extra depth beyond where the mating tooth reaches is the clearance. It's critical.
okay, and the angle of the tooth face. The pressure angle, phi, usually like 14.5 to 25 degrees.
Right. The pressure angle phi is basically the slope of the tooth right at that pitch circle.
What's the advantage of going with a higher pressure angle, say 25 degrees instead of 14.5?
Well, it's a significant trade-off in design. A higher pressure angle gives you a tooth that's wider at the base. It's just physically stronger, so it can carry more load. And crucially, it's much less likely to suffer from undercutting when it's manufactured.
Undercutting. Remind us what that is and why it's bad news.
Sure. Undercutting is when the cutting tool, like the hob, actually cuts away material below the intended involute profile, right near the root of the tooth. It essentially weakens the tooth right where the bending stress is highest. Not good for fatigue life.
Okay, so higher pressure angle means stronger root, less undercutting risk. What's the downside then?
The potential downside is often in the operation. Higher pressure angles can sometimes mean a lower contact ratio.
Fewer teeth sharing the load at any given instant.
Exactly. And that can lead to running that's a bit rougher or noisier compared to gears with a lower pressure angle, all else being equal.
Right. Okay, let's broaden out from geometry to the different types of gears, starting with the most common one, the spur gear.
Spur gears, yeah. They're the foundation. Simplest design, easiest to manufacture. Their teeth are straight, parallel to the axis of rotation.
And importantly, the loads they put on the shafts.
Purely radial loads, just perpendicular to the shaft. That makes choosing bearings much simpler.
But if we need more strength or quieter running, We look at helical gears.
Correct. Helical gears have teeth cut at an angle, the helix angle, usually somewhere between, say, 10 and 35 degrees. Because of that angle, the teeth engage more gradually. It's not an instant full-width contact like a spur gear.
And that gradual engagement gives them the edge in strength and noise.
Yes. They are stronger and run much more quietly than a spur gear of similar size.
But engineering is always about trade-offs. What's the catch with helicals?
Two main things. You lose a tiny bit of efficiency compared to spurs, though it's usually small. But the big one is that the angled teeth create an axial load, a thrust load, along the shaft axis.
So now you need bearings that can handle both radial and thrust loads.
Precisely. It complicates the bearing selection and the overall support structure design quite a bit.
Is there a way around that thrust load?
There is. For really high torque, you can use double helical gears, often called herringbone gears. They look like two helical gears back to back. The opposing helix angles cancel out the thrust loads. Very effective, but more complex and expensive to make.
Okay. What about when shafts aren't parallel? If they need to intersect, maybe at 90 degrees?
Then you need bevel gears. They're shaped like sections of cones instead of cylinders. They're very efficient, too, usually operating in that same high 90% range, letting you transmit power around corners, essentially.
And there are variations here, too, like spiral bevels.
Yes. Spiral bevels have curved teeth, similar to how helical teeth are angled on a cylinder. They run quieter than straight bevels, but are slightly less efficient. And then there are hypoid gears. These are a special type of spiral bevel where the shaft axes don't actually intersect, they're offset.
Offset. Why would you want that?
The most common reason is in automotive rear axles. It lets you lower the drive shaft, giving more space in the vehicle cabin. Hypoids are standard in most rear-wheel drive car differentials.
Fascinating. Now, all these designs depend critically on the material. You mentioned AGMA grades.
Right. AGMA classifies gear steels generally into grades 1, 2, and 3 based on quality and things like material cleanliness.
And beyond the base material, heat treatment is huge.
Oh, absolutely critical. You have two main approaches. Through hardening, where the entire tooth is hardened to a consistent level, maybe like Rockwell C42. Or you have case hardening. This gives you a very hard outer surface, maybe Rockwell C60 or even higher, but leaves the inner core of the tooth softer and tougher.
And why leave the core softer? What's the advantage there?
That softer, tougher core gives the gear better resistance to shock loads. It can absorb impact without fracturing. Meanwhile, the super hard case provides the wear resistance and the high surface strength needed where the teeth actually match and carry the load. It's often the best of both worlds for demanding applications.
Okay, let's put on our engineering hats. We've got a design challenge.
Lay it on me.
We need a spur gear set. It has to handle 100 horsepower. The pinion's running at 1,000 RPM. We need roughly an 8-to-1 speed reduction, and we want to use 25-degree pressure angle teeth.
Okay, 100 horse, lops 1,000 RPM pinion, 8.1 ratio, 25-degree phi. First step, teeth numbers. With a 25-degree pressure angle, AGMA says we need at least 14 teeth on the pinion to avoid that undercutting problem we talked about.
So 14 minimum. Let's be safe. Maybe start with 17.
Good call. Starting with 17 teeth on the pinion gives us a safety margin.
Okay, 17 pinion teeth. An 8-to-1 ratio would mean 17 times 8. That's 136 teeth on the gear.
Mathematically, yes. But we need to consider wear life. We need what's called a hunting ratio.
The hunting ratio. Explain that again.
See, 136 is exactly divisible by 17. That means the same pinion tooth would mesh with the same gear tooth every 17 revolutions of the pinion. That concentrates wear in specific spots, not ideal.
So you want the numbers to be relatively prime, not sharing common factors other than 1.
Exactly. So instead of 136, let's try 135 teeth on the gear. 135 and 17 don't share any common factors. Now, every tooth on the pinion will eventually mesh with every tooth on the gear, spreading the wear evenly.
Okay, so our actual ratio is a 135 divided by 17, which is about 7.94 to 1. Close enough to 8.1.
Yep, usually acceptable. So 17 and 135 teeth it is. Now, the rating. How do we know if it can handle 100 horsepower?
AGMA says check 2 things: bending strength.
Right, which is basically asking if the tooth will physically snap off at the root.
And pitting resistance.
And pitting is about surface fatigue, tiny cracks forming on the tooth face due to repeated contact stress.
Which one usually governs the design in practice?
For most industrial gears, especially at decent speeds, pitting resistance is almost always the limiting factor. The surface gives out long before the tooth breaks.
So we really need to focus on the pitting resistance horsepower calculation, the P sub AC. That AGMA formula looks pretty intense.
It is complex, yeah.
Lots of factors. But conceptually, what really drives the P sub AC rating? It boils down to a few key things. First, The allowable contact stress, S sub C, that's purely down to the material strength and heat treatment. Higher S sub C, higher power. Second, the pinion pitch diameter, D. Bigger gears can handle more load. Power scales roughly with the diameter squared, actually.
Diameter squared, so size matters a lot.
Hugely. And third, there are factors related to the geometry and material elasticity, like a term called the elastic coefficient, C sub P, and the geometry factor I. Okay, C sub P accounts for how stiff the materials are.
Yeah, basically how much the teeth deform under load when they mesh. Steel on steel has a certain C sub P value.
So back to our 100 horsepower example. Let's try some materials, say AGMA grade 1 steel. We could use a basic through-hardened steel, maybe Rockwell C42,
Oh, okay.
or a better case-hardened steel, Rockwell C60 on the surface.
Right, the case hardened is significantly stronger, higher allowable stress, higher S sub C.
Let's pick a starting tooth size, say a diametral pitch, P sub D, 7000. What horsepower can we get?
Okay, running the numbers. With P sub D equals 7, the through-hardened RC42 steel. Nope, it only gets us about 71 horsepower. Not enough.
And the stronger case-hardened RC60 at the same P sub D of 7.
Better. That gets us up to about 92 horsepower. Closer, but still short of the 100 horsepower target.
So neither material works at that tooth size.
Right.
We need more power capacity. What's the lever to pull?
Remember, power scales with diameter squared. The easiest way to boost the rating is to make the teeth physically bigger.
Bigger teeth means a lower diametral pitch number.
Exactly. We need to decrease P sub D. Let's take the cheaper through-hardened RC42 steel. How low does P sub D need to go to hit 100 horse? Cranking through the calculation. If we drop P sub D down to 600, that makes the pinion diameter significantly larger, and that design gives us about 112 horsepower, safely over the 100 horsepower requirement.
Okay, so even though the RC60 case-hardened steel is stronger, we could meet the spec with the lower-cost RC42 steel simply by making the gear physically larger. P sub D equals 6.0.
That's often the case. Size can compensate for material strength up to a point. And pitting, not bending, was the limiting factor in all those calcs.
So the final choice might come down to cost versus size and weight. The P sub D equals 6.0 design with RC42 works. It might be cheaper.
Precisely. That's the engineering trade-off.
Now, once we have a baseline design like that 112 horsepower one, engineers rarely stop there, right? Optimization is key.
Always looking for improvements, yeah. Especially if, say, the customer later needs a bit more power but can't change the overall gearbox size or center distance.
So, stuck with the same basic envelope, what tricks can we use? You mentioned something called a long addendum design.
Ah, yes. That's a clever geometry tweak. You basically modify the tooth proportions slightly. You make the pinion tooth addendum a bit taller and the gear tooth addendum a bit shorter while keeping the overall working depth the same.
So you're just shifting the tooth height slightly between the pinion and gear. What does that do?
It does two very useful things. It tends to make the pinion tooth stronger in bending, and it often improves the surface conditions, reducing pitting stress. It changes that geometry factor we mentioned.
How much difference can it make? Let's say we had a baseline 115 horsepower spur gear design.
Applying a standard long addendum modification to that 115 horsepower design, purely through changing the geometry factor I, could easily boost the rating to something like 131 horsepower. A significant jump with no material change.
Wow, just from tweaking the tooth heights. Okay, what about materials? If we stuck with the baseline geometry but upgraded the steel, say from a grade 1 RC60 to a top-tier grade 3 RC60?
Now you're talking pure material strength improvement. Grade 3 steel allows a much higher contact stress, S sub C. For grade 1 RC60, S sub C might be around 180,000 psi. For grade 3, it could jump to maybe 275,000 psi.
And the impact on power rating, that 115 horse design.
With that jump in S sub C, the rating would shoot up dramatically. You could potentially get up to maybe 268 horsepower from the same size gear just by using the higher quality steel.
Huge difference. Okay, one more option. Change the type of gear. What if we replace that 115 HP spur gear with a helical gear, say with a 30-degree helix angle?
Going helical. Now the improvement comes mainly from better load sharing due to the angled teeth and gradual engagement. Again, it improves the geometry factor I. That 115 HP spur gear replaced with a similar size 30-degree helical might jump up to around 222 horsepower.
So helical gives a big boost too.
But now you have that axial thrust load to deal with, which the spur gear didn't have. Again, trade-offs.
It's clear these calculations are precise, and they rely on achieving that perfect involute curve or those complex helical or bevel shapes. How is that actually done in manufacturing? How do we guarantee the shape?
Well, it's less about drawing the shape perfectly and more about generating it through a controlled kinematic process. It's really quite elegant mathematically. We model the manufacturing process itself. Imagine the cutting tool, maybe a rack-shaped cutter for hobbing spur gears, or a conical cutter for bevels rolling in perfect mesh with the gear blank. The actual tooth profile created on the blank is the boundary, or the envelope, traced by the surface of that cutting tool as it moves.
So the final shape isn't static, it's the result of this dynamic interaction between the tool and the blank.
Exactly right. The fancy term for it is the envelope of a one-parameter family of curves. Engineers use this math to simulate the cutting. They solve equations representing the cutter's surface simultaneously with the constraint equation related to the gear blank's rotation. The solution to that system of equations defines the precise, complex tooth profile that will be generated.
So we've really seen that designing gears that last is this delicate balancing act.
It really is.
Small tweaks in geometry, like the long addendum or changes in material grade, can have massive impacts on power capacity. And often, it's not about preventing the tooth snapping off, but preventing that microscopic surface damage to the pitting.
That's the key takeaway for most industrial gears, yes. Pitting is usually the life limiter. And especially when you get into high-performance gears like spiral bevels and hypoids, the complexity goes up another notch. The exact tooth surface you get, and therefore its performance in life, isn't just defined by the blueprint dimensions. It's critically dependent on the precise kinematic settings used on the specialized gear cutting machine.
Okay, so here's a final thought for you to chew on based on that. If the actual functional geometry of a high-performance gear is determined less by the CAD drawing and more by the specific complex motion settings of the manufacturing machine, where does the design truly happen? Is it in the engineer's software, or is it on the shop floor when those machine settings are dialed in?
That's a fantastic question.
Maybe the future really lies in CAD systems that don't just draw static shapes, but can fully simulate that complex 3D envelope generation process, predicting and preventing failures based on the actual manufactured geometry before a single chip of metal is even cut.
I think you've hit the nail on the head. That's where the cutting edge of gear design and analysis is heading.